There we go. Good afternoon. Thank you all for coming. Gotcha. So as Elad explained, I'm a refugee from mathematical academia, and about 5 years ago I turned to data science and machine learning, where I've been working for the same company, Lateral, doing machine learning for text applications. But there's nothing corporate about today's talk. It's supposed to be a fun introduction to machine learning from a slightly different perspective. So why don't I begin by motivating the fun side? It's cool. So what I'm going to talk about is solving very simple substitution ciphers where you replace letters to make messages unreadable with an algorithm. And one reason this is cool is because it's going to turn out to be machine learning, but from a slightly different perspective. So typically in machine learning applications, for example, if you have a neural network, you're optimizing over a continuous space, a very high-dimensional real vector space, for example, and you're doing something like gradient descent. Here, it'll turn out that the parameter space over which we're optimizing is discrete, precisely because it's the set of alphabets that encode messages. So that's one interesting difference from a typical machine learning application. But from an applied perspective, it's also cool. And one of the reasons it's cool is because there still exist undeciphered, really old manuscripts that historians are interested in and would love to read but can't. So possibly the most famous of these is the Voynich manuscript, named after a guy called Wilfrid Voynich, who originally came from Poland, born in the latter half of the 19th century, went via Siberia to London, ended up in New York as a rare bookseller of all things, got his hand on this manuscript via his wife. No one could read it. He couldn't sell it. He eventually donated it to Yale. And we figured out in the meantime that it's very old. It dates back to the early 1400s. And no one knows anything about it. It looks like it's kind of a natural script. It could be deliberately enciphered. It could be an example of a forgotten language. Or it could be a known language in an unfamiliar alphabet. Nothing is known about this whatsoever. So having got you as excited as I am, I hope, by the way, it's not just text. There are some cool illustrations there as well. So we see things that look like sunflowers. There's a picture of what looks like Roman baths there on the right. Nonetheless, the pictures don't seem to help people be able to decipher it. Okay, so very cool problem, but I'm going to begin with a disclaimer. So first of all, the version of this problem I'm going to solve is a toy problem. It's nothing like as ambitious as decrypting arbitrary historical texts. And so the assumptions that go into the machine learning algorithm will be artificially simple, just to make it tractable. So let's begin a talk. And secondly, as a result, it's not original research in any way. So here's what's going to happen. First of all, I'm going to introduce some notation and define some stuff. Secondly, on the basis of that, we can frame the problem precisely to a degree of precision that a computer could solve with machine learning. Thirdly, I'll say, okay, what does a naive solution look like? How would you sort of try and do this at first? And that'll form a sort of skeleton pseudo-algorithm on which I put meat later when I talk about the maths and stats tools that are necessary to flesh that out. And lastly, I'll turn the naive solution into a proper algorithm that I'll go through step by step with you. So we're talking about encryption and decryption. What is that? I'm going to take a very naive examples-based explanation. We have plain text on the left, which humans can read, and encryption and decryption are inverse processes, which take plain text to ciphertext, unreadable text, and back. So very simple example. The cat sat on the mat. I'm going to map T to U, and H to I, and E to F, and so on. And I think maybe you've got the pattern by now. And that's going to be my ciphertext. So in general, with encryption and decryption, you've got to do two things to choose an encryption scheme. You've got to, first of all, choose an algorithm. So in this case, it's a monoalphabetic substitution cipher, or mask for short. And that's just the algorithm in which I replace each plain text letter with a single fixed ciphertext letter. It's as simple as you can imagine. So that's the algorithm. And then the details of that algorithm, which letters in particular, well, that's called the key. So here I've got the encryption and decryption keys. They are, of course, reverses of each other. A goes to B in the encryption scheme, and then B goes back to A with decryption. So because there are two components to a cipher scheme, encrypting and decrypting involve two choices in general. You've got to choose your algorithm, then choose your key, or deduce those if you're going in reverse. So just to highlight the important stuff here, so I've got this word monoalphabetic substitution cipher, which just means replacing single plain text letters with ciphertext correspondence. They're called masks, and that's the only kind of cipher I will talk about for the rest of this talk. So let me frame the problem now, and I'll begin by writing down some assumptions. So the first of these is artificially, let's assume that we've been given ciphertext by an enemy, but we know that it's encrypted by one of these simple masks. So just exchanging letters. Secondly, I'm going to assume that we have enough ciphertext. I've put it in scare quotes because I haven't defined it, but that will be in a suitable statistical sense that I'll expand on later. And thirdly, I want the punctuation to be stripped from the plain text, just to make things simple. And importantly, I'm going to specify that the spaces between the words are preserved. That's because it'll turn out to be important what the patterns of characters are within words themselves, and we need to know the boundaries. So lastly, and this is also applicable to the machine learning assumption, I'm going to assume that we know the source language, very artificial, so totally unlike the Voynich manuscripts. So we know, for example, that it's written in English, even though we can't read it. And therefore we have access to text from the source language. Not exactly the text that we're looking for, that would be cheating, but to any other sample of text we might care to find. What are the consequences of these assumptions that help us? Well, first of all, 1 and 2 just make the problem feasible. If we don't have enough text, we can't solve it. And I don't want to be iterating over all sorts of possible cipher schemes to explain a sort of toy example here. As a consequence of 3, we can use statistics on character sequences, as I was talking about before. So we know which letters belong to which words. And then lastly, because we have access to the source language, we can take an arbitrary sample of that and use that as training data for a machine learning algorithm. So that's why I've made these assumptions. Those are the consequences. And before I frame the task, I'm just going to give you a little 101 refresher course on permutations. If you've done computer science or mathematics, you've seen this all before. But from a really elementary perspective, a permutation is just a rearrangement of distinct objects. So think people in a line. The people are all different, and the order is important. Who gets coffee first? For us, however, the permutations will always be on letters. They'll be on the alphabet in which we write the texts. And from a more mathematical perspective, a permutation is just a one-to-one map from a finite set to itself. How do we write them? Well, there's different notations. There's an arrow diagram, which is perhaps most explicit but also most bulky. So things from the top map via arrows to things on the bottom. We have an A mapping down to B, B to C, C back to A, and so on. D remains where it is. This is, of course, just a Python dictionary, if you like, so we can express the same thing with slightly different notation. But the notation that's most interesting for me and most useful later on is the cycle notation, by far the shortest. And what it means is that if a sequence of letters is in brackets, then each letter maps to the one after it. So A maps to B, B maps to C. C is at the end of the bracket, so it goes back to the beginning. So in fact, that green cycle is representing exactly the same permutation as you see in the arrow diagram. What happens to D? Well, it's on its own. You could leave it there in a single bracket, but by convention, we just omit it. So if ever you see a permutation with a letter missing, that's because it's the identity on that letter. All right, so here's a final simplifying assumption to the problem that makes the problem a little bit easier to talk about, but it's not significant in any statistical sense. So the observation is that in general, the ciphertext alphabet and plaintext alphabets could be different. So if your enemy is particularly perverse, they might give it to you in an unfamiliar script like this. The cat set on the mat might be in Wingdings, for example, and you don't know about the Wingdings alphabet. Well, I'm going to say that because we've assumed we're dealing with a monoalphabetic substitution cipher, we can make a simplifying assumption at this point here. So monoalphabetic substitution ciphers map single plaintext letters to single ciphertext letters. It's a one-to-one correspondence. So let's do the following pre-processing trick to get out of Wingdings land. What we're going to do is write down the obscure alphabet in any order we please, and write down the plaintext alphabet in any order we please. We've got access to the plaintext alphabet because by assumption we have access to the language in which the plaintext is written, and therefore we know it's standard alphabet. So here's an arbitrary one-to-one correspondence here. Doesn't matter what it is, we could have done it in any other order. And then we're just going to replace the unfamiliar letters with the familiar ones. So here we go. I got something on the right-hand side that I can now sort of read, but it's equally meaningless. Now you might say, Steve, isn't that cheating? And I would say, well, no information has been lost. We could always reverse it back to the obscure alphabet if we want. And the problem is no harder or easier statistically. But it does have the nice simplifying assumption that we can say the ciphertext and plaintext have the same alphabet, and therefore what we're really looking for is a decryption key, which is a permutation of that alphabet, just one single alphabet. Okay, so now I can finally frame the task that I'm going to give the eventual machine learning algorithm. We're given a space-preserved, mask-encrypted ciphertext I'll call C. We know the source language and the name of the alphabet is A. We got a training sample T of text from that language, not the same as the plaintext, but from the language nonetheless. And the goal is to find the decryption key K, which we can assume is a permutation. So there's a little bit of notation. I'm going to say, if we've got a decryption key and some ciphertext, then applying K to that ciphertext is just the current best effort to ciphertext. So this K of C just means what we think is the deciphered text at the present moment in the algorithm. All right. So we framed the problem. I've told you what encryption and decryption is. I've told you the assumptions and so on. Let's get to the whiteboard and sketch out a naive algorithm. And this is very naive indeed. It's a one-liner, and it's woefully underspecified, but here we go. So my initial idea, is that we're going to iterate over all the permutations of the alphabet until we get the correct answer. That's it. So if I had to do a coding interview and write that down in steps on the whiteboard, it would look something like this. You've got to start somewhere, so why don't we start with the identity permutation in the alphabet A? So the thing that maps A to A, B to B, C to C, leaves everything alone. Well, then I'm going to iterate over all the permutations, and for each permutation, pi, for example, here's what I'll do. So if pi of C is more similar to T than K of C is similar to T, then something's going to happen. But that's already a bit computer codey, so let me unpack that into English for you. What I'm really saying is, if the new decrypted text, the decrypted text coming from my second key pi, is more similar to the training text than the old decrypted text, in other words, K of C, then I'll do this thing. But another even simpler way of explaining that line is if pi is a better key than K. That's all I really want to specify. Okay, well, if so, what do? I update the key. Pi is better than K, so let's make K equal to pi. And once I've iterated over all the permutations in the alphabet, well, I'm going to return this key K, which has presumably been updated a few times along the way. All right, so that's my first effort, but there are a few problems with it, 2 to be precise. So the first problem is this one here. I've blithely said that I'd like to iterate over all the permutations in the alphabet, but a typical alphabet, even one that's pretty small, like the Latin alphabet in which we write English, say has 26 letters, and the number of possible permutations in those letters is 26 times 25 times 24, and so on. And that turns out to be 4 times 10 to the 26, so 26 zeros on the end. And I figured out, using a Python notebook, that if you decrypted 1 million, or if you checked 1 million of these keys per second, it would still take you 13 trillion years to iterate exhaustively over those permutations. So lovely, simple algorithm, but too naive to work in finite time. Well, in time you're prepared to wait. So problem number 2 is a semantic one. It's that we don't know what similar means, or rather, we don't know how to tell the computer what 2 similar texts should look like. So these are the 2 major problems with this naive approach. And the rest of my talk will be unpacking solutions to those problems, feeding them back into the algorithm to making it more precise and explaining what that is. But just so I can foresee or presage what these solutions are, you have a little North Star to aim for in the talk. Let me vaguely explain what they are. So the first one we're going to solve not by iterating over all the permutations of A, but by picking a sensible iteration step, a little bit like the way you step update in stochastic gradient descent in the real case, to pick correct permutations from a huge possible space. I'll explain what that means in much more detail later. And then the second solution will be similarity for our machine will be encoded in letter sequence frequencies. Okay, so and what that means is when we glue the 2 precise explanations of those ideas together, we can build a nice machine learning algorithm. So on to the next section. We're going to do a little bit of maths and stats, but it's simple stuff. So the first idea I'll need is that of an n-gram. So an n-gram for me just means a sequence of n letters that's not interrupted by a space. So it's inside a single word. So sometimes people use n-grams to mean words in a sentence. I don't mean that. I mean characters in words. Okay, so for example, the cat, again, is sitting on the mat. The 1 grams would just be the letters in order, and there the spaces don't really matter at all. The 2 grams, well, that's the sequences of 2 letters. You've got TH and then you've got HE. Because there's a boundary between the and large, the next bigram or 2 gram is LA and so on. And 3 grams work the same way. So that's just what an n-gram is. Now, what's interesting or important about them? Well, to give you a sense of why they might help encode a text in a way that helps you write a machine learning algorithm, I've done a little data visualization experiment here. So this is called Bigrams in the Wild, and what I've gone out and done is taken a German Wikipedia article, and it happens to be the article for cryptography, and I've computed the bigram frequencies, so 2 grams, sequences of 2 letters, and because it's 2 grams, you can arrange them in an array, where the rows of the array correspond to the first letter, and the columns of the array correspond to the second letter. Done a little bit of pre-processing to make it 26 by 26. German has umlauts like U, so I've replaced that with UE. Everything's fine, and I get something like this. So unfortunately, you probably can't read the letters in the tiles there, but it's indexed both rows and columns by the standard Latin alphabet. And to give you a sense of that, let me just point out that that glowing one there is EN, so it's in the eth row and the nth column. Okay, where's the color coming from? Well, this is in fact a heat map of a frequency matrix. So the secret matrix code, in the sense of the film as well, behind this picture, is a two-dimensional array with real number entries. And I've just got a heat map which says that yellow is really hot and therefore high real number, and blue is really cold, therefore low. So I'm going to sort of suggest that this is kind of like a fingerprint for the German language. It tells you that EN, for example, is a really common bigram, as is ER, which is the other yellow one there. And almost all the other bigrams don't appear most of the time at all. So it's a highly non-uniform distribution and very specific. So let me expand upon that a little bit more. Bigrams are kind of like fingerprints for natural languages, in the sense that they're stable within a language, so it doesn't matter which sample of text you pick from within German, for example. But they also vary between languages. So German and English bigrams are quite different. Let me give you an illustration. So I won't label the rows and columns of these bigram heat map matrices just yet, but I want you to observe that on the left-hand side, the top and bottom matrices are visually quite similar. If you squint your eyes, they're almost indistinguishable. And on the right-hand side, they're quite similar as well. You see that you've got those 2 yellow tiles repeated, but not quite the same. So they're similar because the left-hand matrices come from 2 English sample texts, and the right-hand matrices come from 2 German sample texts. They're kind of like fingerprints. Or rather, they're different. But the rows are similar to each other within each column, even though the 2 sample texts are quite different. So I've taken the Wikipedia entry for ancient Rome in both languages for the top row, and the Wikipedia entry for cryptography in both languages in the bottom row. So they're 2 very different, thematically very different texts, and nonetheless you have this similarity of bigram patterns, which I find quite fascinating. I'd never visualized this before until I prepared this talk. And in fact, I wrote the algorithm before I did this visualization. It's kind of neat. All right, so what's the punchline here? Why am I showing you these pretty heat maps? Well, I'm going to suggest that proxying a text by its matrix of bigram frequencies is a really good featureization for a machine learning algorithm. So in practice, it'll be the 2-dimensional arrays of real numbers behind these things. But if I'm going to do that, because my problem is to decrypt a mask cipher, and because a mask cipher is essentially a shuffling of the alphabet, I better know what happens to the matrices when I shuffle strings by exchanging letters with each other. So let me show you what happens using an example. The cat is again on the mat, and to simplify things, I've taken as my plain text alphabet exactly those letters that occur in the plain text. There are 9 distinct ones altogether, and the key looks like this. So we see that A maps to H, and C maps to E, and so on. So the question is, what happens to the bigram matrices when you apply a mask encryption? So let me just work out the one on the left-hand side, 9 by 9. The top right-hand corner, that yellow thing there is AT, which is, as you might expect, because it occurs in cat, sat, and map 3 times, much more than anything else. And what I'm going to do now is just work out the bigram matrix for the ciphertext on the right-hand side, thing we can't read. Okay. And I'm going to show you that it's really just a shuffle of the original matrix. And what I mean by that was, first of all, just notice that it's the same set of colored tiles just rearranged. Right? Your eye can see that straight away. But it's a shuffle in a more precise sense, in that it comes from the permutation. And let me explain with an example. You might have seen this already, actually. But let me focus just on one tile to illustrate what's going on. So this AT, which occurs most frequently in the plain text here, well, that maps over to HN. That's the yellow thing on the right-hand side. Well, why is that? That's just because A maps to H, like the key tells us, and T maps to N. There's no surprises there. But what that means is that the 8th row has been mapped over to the H row on the right-hand side, and the Tth column to the Nth column. In other words, the rows and the columns are being shuffled exactly according to the permutation. And that kind of makes sense, because a mask relabels the bigrams just by shuffling the letters. And so that's going to have the same effect of relabeling the rows and columns of the matrix. And when you write them back out in alphabetical order, you're applying exactly the permutation that the key gives you. Okay, so I've dumped a lot of information about permutations and n-grams onto you now. So I just want to spend a slide kind of summing up as to why we want to use a bigram matrix in our machine learning representation here. So the first thing I said is maybe we could represent a text by its matrix of bigrams. And the second thing I pointed out was this fingerprint slide, that 2 texts from the same language have similar representations, even if the texts themselves have nothing to do with each other. So what's the punchline here in a machine learning context? I'm going to use that particular fact, these similar representations, in this particular context. So I'm going to say, well, that means that the plain text and the training text have to have similar bigram matrix representations, right? Because by assumption, they come from the same language. Someone has told us that the cipher is in English, so I go out and I download any Wikipedia English article I want. I still can't read the ciphertext, but I know whatever that plain text is, it's in English, and so its matrix of bigrams will have to resemble the matrix of bigrams of the training text. It's really important. And then the last thing I told you was, well, mask encrypting your plain text is really just letter substitution, and that corresponds to row and column permutation of the corresponding bigram matrices. So I'm going to illustrate that here by just saying, well, the ciphertext is some rearrangement. In this case, I've just taken a rotation or something. So we're trying to pick a permutation of rows and columns which take us back to something looking like the training text, which will therefore, by the first row, be something looking like the plain text. That's the chain of reasoning here. So I'm really interested in this shuffle P of the rows and columns of the ciphertext matrix. So in other words, decryption is exactly the process of finding and applying that permutation P. Okay, so so take a step back. With the naive algorithm solution, I suggested there were 2 problems. Right? The first problem was that there are way too many permutations to iterate over exhaustively. And the second problem is that it's not clear what a similar cipher and training text should be to a computer. So I've addressed the similarity problem by saying we can turn text into bigram matrices and see if the bigram matrices are similar as a proxy for the similarity of texts. Right? That's tick. That's why I did all the heat maps. But I still haven't told you how we solve the exhaustive iteration problem. And in order to do that, I'm going to have to give you 3 simple facts about permutations so we understand them a little bit better. And then that'll tell us at the end what a kind of atom is in the permutation world. In the same way that if you are looking at whole numbers, at integers, the atoms are sort of prime numbers because every number is made up out of multiples of those. I'm going to find out what an atom is in the permutation world. So that's where I'm heading here. So here are the 3 facts. Every permutation is a product of cycles. So if you don't know exactly what that means because I haven't said what a product is, I'm going to tell you by example. So here's a rather complex-looking permutation on 6 letters, except that it's not as bad as it initially looks, because if I highlight it like that, you can see that A and D have been exchanged among themselves. So B, C, E, and F must be doing their own thing as well. And it turns out if you write this in my favorite cycle notation, you get AD as a cycle, no surprises there, but you can tease out that B maps to E maps to C maps to F, and F maps back to B. And the important thing to note there is that both of those things in the brackets are cycles. You're just shifting things along until you get to the end, and then you go back. Right? So I've taken this complicated thing, and I've written it out as a product of cycles. Let me suggest an analogy that will help you sort of grip onto that. If permutations are like the world of all matter in physics, then cycles are kind of like molecules. And we're really saying that matter can always be broken down into molecules. Right. The second thing that I'd like to point out is that every cycle is a product of transpositions or swaps. And a transposition just means swapping 2 letters. So, for example, A and D, swap. That's it. Okay, and that in metaphorical terms, is kind of like saying every molecule can be broken down into atoms. So I've told you all matter is made of molecules. All molecules are made of atoms. So all matter is made of atoms. It's one of those Greek philosophical syllogisms. And for us, that means every permutation is a product of transpositions. So let me just illustrate that cycles can be broken up into transpositions, which is maybe the hardest thing that I've suggested here, by an example. And then I'll suggest how the example generalizes. So I've taken a simple example on just 4 numbers. It's the cycle 1, 2, 3, 4. You send 1 to 2, 2 to 3, 3 to 4, back to the start. And I'm asserting it can be broken up in the way on the right-hand side. So permutations, just by convention, are multiplied from right to left. So what the right-hand side is saying is that, first of all, you swap 1 and 4, and then you swap 2 and 4, and then you swap 3 and 4. Let me show you that this really works with a picture. So firstly, let's just apply the whole thing. So you take the sequence of letters 1, 2, 3, 4, apply the cycle permutation, and it just moves everything along. There's no surprises there. But secondly, why don't I, from right to left, just apply all the swaps that I've said? Well, let's highlight them in green so they're more visible. You've got 1 being swapped with 4, then 2 being swapped with 4, and finally 3 gets swapped with 4. And you can see that we get right back to where we started. So you might say, well, I don't quite trust you, Steve. You're a sneaky mathematician. You might have picked an example that works, but it doesn't generalize. But the interesting thing is, this is a particular pattern that really does generalize. Because let's look at the shape of that decomposition there. So swapping 1 with 4 is really saying let's swap the first and the last thing, whatever those 2 things are. And swapping 2 with 4 is like the second and the last thing, and then the third and the last thing, and so on and so on. It's a genuine pattern there. And that's what I'm writing here in this general notation, is saying, first of all, you swap A and the Z, and then B and the Z, and so on. Really works. Okay, so I think that's kind of neat about permutations. But the take-home for us is that these transpositions, these swaps, are like the atoms of the permutation world. So what that means is if you have like 10 people in a row and you want to get any rearrangement of them, you can always do it just by swapping 2 at a time. And what we're going to do then is take these transpositions and then apply them to our existing decryption key to just make it a little bit different every time. Just a little bit different, and then we'll check it. And we're guaranteed that we could always get to the right answer because of this decomposition, because you can always build things out of swaps. That's what we're going to do here. So let me, with all of those facts, outline the algorithm. It's a machine learning algorithm, so I'm going to need some notation, and I'm going to need to tell you what an objective function is. Let me assemble all of that first. But first I'll remind you of what the task is. We formulated that a few slides ago. But we're given some mask-encrypted ciphertext C. We know the source language, and we know what the alphabet is. It's all known. We also have access to training text. And then the job is to find a permutation of that alphabet, and that permutation will be the decryption key. All right, so first of all, the formulation of the task gives us some input data. So that's the alphabet, the ciphertext, and the training text, denoted thusly. A little bit more notation. K, as I suggested, is the decryption key. I'm calling it current here because it'll keep getting updated in a for loop in the algorithm, and it's sort of our best guess at each stage. That's all that means. Remember, K applied to C is therefore the current deciphered text. And the only new notation there is M and F, which are bigram count and bigram frequency matrices. So there'll be 2x2 arrays, and for any pair of letters, they'll have an entry telling you how frequently those letters occur in either the deciphered text or the training text. Okay. So here's the objective function. Right? It's a bit intimidating at first. So it's saying, I'll read it out, and then I'll break it down. It's saying we're going to take the product over all pairs A and B in the alphabet, that's that A cross A thing there, of the empirical frequency coming from our training text of that particular bigram to the power of the number of times that bigram appears in the currently deciphered text. It's a whole mouthful, and it's not quite clear what's going on at first glance. So I'm going to take it more slowly. So that thing there is the empirical probability of AB. So it's saying how many times do you expect that to occur based on your training data. And that thing there is the number of times that occurs in the currently deciphered text. So let me give you an example. Let's imagine we're most of the way through the decryption process. So it knows already that AT is quite a commonly occurring bigram. So we have three copies of AT, we'll suppose. And the question is, what's the likelihood that those things occur in the currently deciphered text? Well, AT is a pretty commonly occurring bigram, so let's say it occurs 5% of the time. Well, naively, you might say, well, let's just multiply 5% times 5% times 5%, and that'll give me my 0.05 to 3. And that's color-coded there the way it is to suggest that the 0.05 is the FT as a particular example, and this integer is the number of times it occurs in the currently deciphered text, the green thing there. Okay, now you might say, well, are you really allowed to estimate the number of times these bigrams occur in this naive way just by multiplying them together? Doesn't that suggest they've been independently sampled from some distribution? And the answer is no, I can't do that legitimately because, for example, if you consider the bigrams in the word the, right, the first of them is TH and the second is HE. So already the second letter of the first bigram is constraining what the next bigram can be. So it can't be an independent distribution. So this is, in a sense, an artificial assumption. But nicely, happily for us, it turns out to be good enough to do some learning on. So that's why I have this thing has the shape it does. Okay, so in other words, if you multiply the bottom thing to the power of the top thing, you get the empirical probability of that many occurrences of that particular bigram in the ciphertext. And so the whole product is just the probability that each bigram occurs as often as it does in the deciphered text. In other words, it's a likelihood function. All right, so let me just walk you through the algorithm, and then we're done. Tiny bit more notation. So T is going to be a transposition, one of those two-letter swaps, and PT is a permutation matrix corresponding to that transposition. I haven't defined what that is, so I'm going to show you with a picture. So the identity, if you apply a permutation to the identity matrix, to its rows, and in this case we're swapping the second and third row because it's the permutation 2, 3, then you get what's called a permutation matrix. That's all that thing is there. So kprov is the provisional decryption key. It's just a separate variable that I keep to make sure that I only update the actual provision key if I get a better answer. And R is the number of repetitions in my for loop. So I'm going to start off at the beginning by just setting k equal to the identity, and then I'll compute the frequency matrices ft and fkc. And then this time, instead of looping over all the permutations, which is sort of impossible, I'm going to, for each permutation in range R, just choose at random a swap, and I'm going to set my provisional key equal to that swap times the existing thing. And then what I'm going to do is say, okay, like, has that improved? Has that made my ciphertext more likely? And that's what this matrix multiplication does here. And in order to decide if it's made it more likely, I need to compute the new likelihood function and the old likelihood function and compare them. And if it's more likely, then I update everything. And you do this a whole lot of times, and then you return your key. And that's the algorithm. So I thought I would end with a demonstration. I wrote a little bit of code to implement this. So here we are here, and you can download it yourself and play with it if you want. So let's clear the screen first of all. Okay, so what I got here is a little bit of plain text and a little bit of training text. So the plain text is taken from the New York Times. It's just an article about an Argentinian astronomer who, by accident, observed a supernova while looking through a telescope. That's how it turned out. So that's the thing that's being encrypted. And then the training text here is someone doing a census of penguins in Antarctica using drones. So that's what it's learning on. All right, so I've got a little demo script that does everything all at once. And what it's doing is it's encrypting the plain text with a random key and then storing the ciphertext, and then it passes down the pipeline just the ciphertext, but not any information about the plain text. And it says, hey, use the algorithm I just explained to try and guess. So the algorithm kind of works, but not always. It's not a great algorithm. It's maybe 3 out of 5 times. So we might have to try it a couple of times, but there's a nice visualization along with it. There we go. So here's a little like ASCII art heat map of the updated bigram matrices here. And it's sort of like, it started off with rubbish there, and it's got to boop a star, which should be boom a star. So let's kind of try again. Oh, look, there we go. Okay, so it seems to have got it right. And probably get it wrong again, sort of settled on boop and so on and so on. So that's just straight up Python with NumPy. There's no other machine learning libraries there. It's doing exactly the thing that I was explaining in the talk. Thank you very much for listening.
Thank you very much for a fascinating algorithm. And any questions? Start with Marty. Can you?
Hi. Yeah. Thank you very much for that.
No worries.
This reminds me so much of like good Turing smoothing and the way Turing in the Second World War solved the Enigma code. Is that like? Am I completely off on that, or is there like a clear relation to that?
Yeah, I don't know any of the details about how the bombs worked. All I know is that the code that he was solving is much, much harder than this. So the German...
Yeah, I mean, it was translating German, like decrypted German into unencrypted German, but...
Well, yeah, I guess the point about Enigma is that it's a much, much harder cipher than the one I was using. So I think like the combination space is like orders of magnitude more difficult. Yeah.
I was just wondering about the neat terminal visualization of the bigram matrix.
Yeah.
Is that something you wrote just for this, or is there a library?
Yeah. I think there's something called COLR, like color terminal in Python. So I should have given some attribution to the color authors if they have to be present. Yeah. So it's just a silly little bit of ASCII art.
Should I go? Okay. So thanks for the talk. This is super fun.
Welcome.
Is there anything documented, even on failed attempts, but on applying something like this to the Voynich manuscript that you presented at the beginning?
Yeah, so that's what got me interested in it to start with. I thought like, oh, this Voynich manuscript thing's really cool, but of course it's like way harder than this. So there is a literature of people in the last 30 years or something trying and failing to decrypt the Voynich manuscript with methods like this, but better. And I think the most recent one was like 1 or 2 years ago. So there was a couple of guys that wrote a paper in which they sort of suggested they might have decrypted one sentence from the Voynich manuscript and explained a whole bunch of stuff there. But my sense was that the community of people who really understand this stuff were a bit skeptical and kind of said, like, if you've really got it, you should be able to tell us what the whole thing is and not just one sentence. Yeah.
So do you have a way to measure the success of this, not empirically by running it on a corpus, but rather actually theoretically. And the reason I'm asking is this is a hard problem to solve theoretically in the worst case because it seems like graph homomorphism or one of those, graph isomorphism.
Right.
So I assume it's like computationally hard, but you're dealing with particularly type of text and so on. Is there any kind of theory that can be done on analyzing this?
That's a great question. I don't know. For me, this is just an empirical project. So I imagine that would be really hard. You'd have to, all sorts of bounds that would depend on the amount of training text you had. You have to assume that it came from a certain kind of distribution. There's a whole lot of statistical assumptions you'd need to make about the shape of your training data in order to kind of nail down the problem enough, I imagine, in order to prove something rigorous about it. So that, a fascinating question that wasn't part of my project at all, unfortunately. Yeah.
Anyone else? Okay. So thank you very much, Stephen. Thank you.
Thank you.